Okay, so what have we done now? Well, um, we've started off and we've introduced a number of Hilbert spaces. So let's give these some names. Um, when there's no particles, when we're talking about the vacuum, we've got the Hilbert space. Let's give it curly H for Hilbert and a subscript naught for no particles. Um, we've also introduced the Hilbert space of one particle, gave a basis for that. We've also introduced a Hilbert space for two particles. And the last thing that we did was we introduced a Hilbert space for three particles. Now, in quantum mechanics, if you were, say, studying an atom or an electron, or sure, let's say you're studying an electron, you might be living inside the Hilbert space H1. Perhaps you study a proton surrounded by an electron, so that's some sort of an atom. Then you might be studying a problem in the Hilbert space H2. But the point is, in quantum mechanics, if you start off in the Hilbert space H2, you always remain in the Hilbert space H2. In quantum field theory, I might start off with a very highly excited photon, and that photon could decay into an electron and a positron. So I could start off in the Hilbert space H1, and then because of pair production, I could make a transition into the Hilbert space H2. So when I come to study quantum field theory, I cannot restrict myself to a Hilbert space of a definite particle number. In general, I will make transitions between different Hilbert spaces with a different particle number. So because of that, in quantum field theory, we need to work in what's called the Fock space. And the Fock space is given by the direct sum of all of these different Hilbert spaces that we've been talking about. So you take a direct sum of the no particle Hilbert space, the one particle Hilbert space, the two particle Hilbert space, and so on. This would continue on to infinity. So you'd need to take a direct sum of all of these different Hilbert spaces. So the operation that I'm using here is called the direct sum. In case you want to go and look that up in a book on linear algebra. And what does it mean to take the direct sum? Well, if I was in, say, the two-particle Hilbert space, I would take linear combinations of this basis, P1, P2. So I could take linear combinations of those vectors. If I'm in the direct sum of H1 and H2, I can now take linear combinations of states from the basis of H1 or from the basis of H2. So by taking the direct sum of all of these different Hilbert spaces, I'm saying the basis for Fock space is any state in any basis of these different Hilbert spaces, okay? So I'm allowed to add a state of no particles to a state of 3 particles, to a state of 2 particles, to a state of 40 particles. So the particle number certainly is not fixed. Okay, good. Now I want to start talking about Lorentz symmetry. So how are we going to realize Lorentz symmetry on this Fock space? Well, the first thing that I can imagine is, let me consider some Lorentz transformation lambda. So lambda is some Lorentz transformation. Here, you've seen lots of examples of lambdas by now. So this is some Lorentz transformation. Okay. Let's imagine I've got a particle in my rest frame, and it looks to me like this particle is at rest. It has no momentum. Now you're in a different Lorentz frame. You're moving with respect to me. So if you look at this particle, we don't agree on the speed of the particle. But one thing that we do agree on, we both agree that there's one particle. If I do some Lorentz transformation, I'll change the velocity of this particle. I will see the velocity change. You will also see the velocity change, but we'll still agree that it's just one particle. If we were working inside the three-particle Hilbert space, and we have three particles sitting there, you and I will not agree on what the momenta of those three particles are, but we will agree that there's three of them. And if we perform a boost, we will agree that the momenta of those particles changed and that there are still just three of them. Okay? So the first thing that we can say is Lorentz transformations leave us inside the n-particle Hilbert space. If we've got a state in the n-particle Hilbert space and we do a Lorentz transformation, we still have a state inside the n-particle Hilbert space. Now I'm going to denote the operator that acts on Fock space by U, and it's U of lambda. This is the operator that performs the Lorentz transformation lambda. And when it acts on the n-particle Hilbert space, it gives you a state that's also in the n-particle Hilbert space. Good. Now, this U for the U of lambda, that is telling us U is for unitary. It's a unitary operation. Now, let me remind you what a unitary operation is. So if we've got a unitary operator, U, then one of the things that U obeys is that U dagger times U is the identity. So this equation in the box, this is what it means to be a unitary operator. Now, why are unitary operators important? Well, if you want to make a physical prediction in quantum mechanics, you always do it as follows. You start off with some initial state, and you want to calculate the probability that you will make a transition from this initial state to some final state. Okay? This quantity, this overlap here, this calculates for you the probability amplitude to make a transition from the initial state to the final state. Okay, that's the probability amplitude. So if you wanted to get the probability, you would simply square the probability amplitude. And this is how we calculate all predictions in quantum mechanics, by calculating the overlaps between two states. Now, if I've got a symmetry, okay, I expect this to be reflected in the kinds of predictions I can make. So here's an example of a symmetry. The laws of physics are time shift invariant. So the laws of physics today were the same as the laws of physics yesterday, and tomorrow the laws of physics will still be the same. So in particular, if I have an operator that produces a time translation, then my initial state might be shifted into U times my initial state. Okay? So what I mean by this is my initial state is the state today. U times the initial state is the state tomorrow. My final state would become U times the final state. And in particular, to get bra final state, I have to dagger. So I'll get final bra times by U dagger. If time translations are unitary operators, then final U dagger, U initial. So this is the translation, this is the probability amplitude to make a transition from the initial state to the final state, but calculated tomorrow, because I'm using all of the states that have been shifted to tomorrow. Well, this is nothing but the overlap between the final state and the initial state if we have a unitary operator. So if time translation is implemented by a unitary operator, we know that no prediction of the theory would change, and we're perfectly justified in calling this a symmetry of the theory. We want Lorentz invariance to be a symmetry of the theory, and it is for that reason that we implement the Lorentz transformations as unitary operators. So Lorentz transformations will act as unitary operators on Fock space. We're going to say a lot more about that, and we're going to develop this idea a lot more. But for now, the key point is unitary operators don't change the overlap between two states. And because in quantum mechanics, physical predictions are always given as overlaps between states, it means that unitary operators don't change any of the physical predictions of the theory. If you have a symmetry, that means you have some operation that doesn't change any of the physical predictions of the theory. So it makes sense to implement that symmetry as a unitary operator acting on Fock space. Let me just make one last comment. We know that a Lorentz transformation in the one particle Hilbert space will leave you in the one particle Hilbert space. We also know that if you do a Lorentz transformation in the naught particle Hilbert space, H naught, you will remain inside the naught particle Hilbert space, H naught. But there's only a single state in the no particle Hilbert space, which is the vacuum. So what that tells you is if you do any Lorentz transformation on the vacuum, you get the vacuum back. So the vacuum is actually a Lorentz invariant state, and all inertial observers agree on what the vacuum is. They all agree on what the state of no particles is.